So, welcome back. We're in the middle of taking a little bit of a detour, and the intent of the detour is to get us up to speed in the use of statistical mechanics to think about binding problems. And of course, it serves as a foundation for many other uses of statistical mechanics that we'll find ourselves thinking about in the remainder of the course. So, the point of this particular exercise is that I basically want to do two problems. The first problem that I want to do is the one that we have already done using kinetics, and that is that I have some receptor and I have some ligand, and I want to figure out the probability of making the receptor ligand complex. So our that's our first intent. And then I also want to do an analysis of what I'm going to refer to as, so this will be problem one. And then problem two is I want to think about cooperativity from a statistical mechanical point of view. And what I have in mind there is that I have some receptor that has two binding pockets, and cooperativity refers to sort of an enhanced affinity. Once one of the ligands is bound, the likelihood of binding the next one is higher. And I want to try and talk about where that comes from. So that's the plan, is to do these two problems. So let's start with example number one, which is just the classic binding curve, but now from statistical mechanics. And the plan is we're going to follow the protocol, and now I'm going to do it kind of in diagrammatic form. So I'm going to identify the states, then I'm going to figure out their energy, and then I'm going to figure out their multiplicity, and then I'm going to compute their statistical weight. So that's the plan. And the way we're going to do this is I'm going to imagine some little box, and this is my little universe, and inside of the box I have my receptor, and I'm going to treat this little world, as I've already started doing in the past, as a lattice. And so I'm going to imagine that space is divided up into a series of discrete boxes, my so-called lattice points, and then I'm going to imagine that there are ligands that are distributed throughout this box and kind of at low concentration. So there's going to be L ligands, and there's going to be omega, that's the number of lattice sites, and that's my situation. And so that's the unbound states. And then I'm going to also be interested in the case where one of these guys is bound. So here's the second situation. So just to be clear, this is the example of unbound. These are all the unbound states. And I'll show you right here. And then these guys are the bound states that I'll show you here. So that's the two categories of states. Either the receptor is bound by a ligand or it's not. Those are the only kinds of states that are allowed, and this little universe is closed. So now following the protocol, I need to write the energy. So here, the energy is L times epsilon solution. What do I mean by that? I mean that there are L ligands. Each molecule, when it's sitting in solution, has a certain free energy, which I'm going to call epsilon solution. Down here, I have L minus 1 in solution, and then plus one of the ligands is bound. It has a Velcro attraction to the receptor, and I'm going to identify that as epsilon B for epsilon bound. So that's the energy in that case. Okay? Now, what is the multiplicity? The multiplicity is the number of ways of putting L ligands on omega sites. And that is going to be written as omega factorial over L factorial, omega minus L factorial. If you need to brush up on this, this is something that I talked about in an earlier vignette about the binomial distribution and counting. And so if you go back to that section on probability, you'll find that I worked out these kinds of multiplicities. But here's the essence of it. So you note that for the first ligand, I could put it here, I could put it here, I could put it there, I could put it there. I have omega choices for where I put that first ligand. Once that ligand has taken a spot, then there are only omega minus 1 lattice sites left. So the second one has omega minus 1 sites. We keep doing that until we run out of ligands. And what we'll find is that's equal to basically omega times omega minus 1 times omega minus 2, all the way up to omega minus L plus 1. And that omega minus L plus 1 is actually this. That's another way of writing it. This L factorial downstairs goes back to, you might remember when I was doing the stadium seating, and I had a red and a blue and a green person, and then I'm saying, well, if they are all dressed the same, you can't tell the difference between them, and so you've overcounted. Anyway, so that's where that comes from. So now for the multiplicity of this guy, this is omega factorial over L minus 1 factorial, and then omega minus L minus 1 factorial. And this is approximately equal to omega to the L power over L factorial, and this is approximately equal to omega to the L minus 1 power over L minus 1 factorial. Why is that? Because let's look at this top one. If I have a huge number of lattice sites, let's say I have 60,000 seats in a stadium and I only have 30 people, I could take a hat, I can put numbers of all the 60,000 seats, and I can let person number 1 choose their number of their seat, and then they can put their number back, and I shake it up. And we're not worried about the fact that person number 2 is going to pick the same seat. Why? Because there's 60,000 seats. There's only 30 people that are going to be choosing. So actually, effectively, each person has omega choices. So the total number of choices is omega to the L power, because each person has omega choices. So omega to the L, it's omega times omega times omega. That's all the choices. And then I divide by L factorial because I've overcounted. And so that's the upshot. And so when all the dust settles, then I'm left with the statistical weight, which is the multiplicity times the Boltzmann factor, and that is written as this. So omega to the L power over L factorial. This part is the multiplicity, and this part is the Boltzmann weight. The total statistical weight is the product of those two things. Down here, just because I don't have room, this guy is omega to the L minus 1 over L minus 1 factorial, and then e to the minus L minus 1 epsilon solution plus epsilon b, all divided by kBt. So that tells me the relative statistical weights of the bound and the unbound states. Now, let's say I want to compute p bound, the probability of the bound state. How do I do that? Well, I take the statistical weight of the bound guys, and I put it in the numerator, and then in the denominator, I take that weight plus I take the statistical weight of the unbound states, and I add them all together. So that's what p-bound is. Just as a reminder, when I want a probability, what do? I take In the numerator, I take all the favorable outcomes, the statistical weight of all the favorable outcomes, and the denominator, I sum over all the statistical weights of all of the outcomes. So that's what the concept is, and that's what I've implemented here. So there's two categories of states, and I've multiplied them accordingly. Now, I want to simplify this. And the way that I can simplify it is I can basically, if I multiply top and bottom by L factorial over omega to the L factorial, omega to the L, and then times e to the L epsilon solution, kBt, and I do the same thing downstairs. So I have L factorial over omega factorial, e to the L epsilon solution divided by kBt. If I multiply all this through, what I get is L over omega, e to the minus, epsilon b minus epsilon solution divided by kBt over 1 plus L over omega, e to the minus, epsilon b minus epsilon solution divided by kBt. So when all the dust settles, this is what statistical mechanics tells us the binding probability is. And if you look at this carefully, it invites us to, for example, multiply top and bottom by little v. Sorry, didn't mean it where I put it. Top and bottom by little v, top and bottom by little v. Note that omega times v is v tot of our boxes. So if I have, that implies that L over omega v is equal to the concentration of L. So that's one observation for you. Second observation is that if I make the definition, Kd is 1 over v e to the epsilon b minus epsilon solution divided by kBt, then I have recovered that P bound is equal to the concentration of L over Kd over 1 plus the concentration of L over Kd. This is really huge and interesting. What I'm saying is that we've given a microscopic interpretation of the Langmuir binding isotherm that we worked out earlier, that I worked out using thermodynamic arguments earlier. So, just to remind you, if I were to plot this thing, so this axis is the concentration of L, this axis is P bound, which runs to 1, then the curve is going to look something like this, and this point, this concentration is Kd, and that corresponds to the binding probability of 1/2. In other words, when the concentration is equal to Kd, then the binding probability goes to 1/2. Okay, so with that as our background, I'm going to stop here, and then in the next vignette, what I'll do is I'll revisit this, but now attacking the problem of cooperative binding, and we'll see that adds a little extra interesting nuance. So let's just review what I've said thus far. I've said that we can use statistical mechanics in the form of the classic statistical mechanics protocol, which invites us to identify the microscopic states, to figure out their energies, to figure out how many different ways there are of realizing each energy, and then together that gives us the statistical weight. And then with the statistical weight in hand, we can compute the probabilities by taking in the numerator all the things that are favorable, they're the things we want the probability of, divided by the statistical weight of everything. So that's the concept, and where that led us to was a reconciliation of the thermodynamic interpretation of binding, which is in the language of concentrations and KDs, and the microscopic interpretation of binding, which is in the language of number of ligands, which I called L, the size of the lattice, and then energies, binding energies, which is very interesting. In other words, we've got a recognition that the KD depends on the binding energy. You can see here, if you think about it, the smaller KD is, the stronger the binding. And So epsilon b is smaller than epsilon solution. So this thing up here is negative. So I have e to the minus something, which is going to cause, the larger that something is, the smaller kd will be. So the more tightly bound something is in terms of epsilon b, the more negative epsilon b is, the smaller kd will be. And they're exponentially related to each other. So that's what I have to say about this category of binding problems.